Alright, hi. In this video, I want to discuss in a very simple and a concise manner the representation of a wave function in the context of quantum mechanics in momentum space. You see, in classical mechanics, we have a very simple way of describing the trajectory of a particle. For example, if I take the example of a spring mass system, then we are usually interested in studying the position of the particle versus time. So we want to understand how the position of the particle changes with time. Sometimes we are also interested in studying how the velocity or the momentum of the particle changes with time. And in some cases, we are interested in removing this time parameter and only looking at how position and momentum changes with respect to each other. And these diagrams are usually called phase space diagrams. Now, this is the classical context of studying the evolution of some kind of a mechanical system. However, when we go from the classical systems to quantum mechanics, that is where we discover that the way of understanding the evolution of a particle's trajectory is completely different. Because we don't have a very simple correlation between momentum and position or the time derivative of the position of a particle in quantum mechanics. Instead, in quantum mechanics, what we have is a wave function. You are familiar with this. So we have what is called the wave function, which is a function of the position for a particle which is restricted to 1D. I'm going to write it as x, and time. Now, this wave function is an abstract mathematical function that contains the information about the particle's evolution as the particle is moving around. So, from here we can figure out the probability density of the particle, we can find out the average values of the position, the average values of the momentum, the average values of the energy, etc., etc. However, there is another quantity in the context of this formulation, which is known as the wave function of that same quantum mechanical particle, but which is a function of momentum and time. This is also a function of that particle's evolution, but instead of being a function of position, it's a function of momentum, and this can also give us an idea about the probability density of the particle's momenta and the average values associated with its momenta, position, etc., etc. Now, these two quantities are very interlinked to one another. The wave function in position space and the wave function in momentum space are very much interconnected to one another. One is the Fourier transform of the other. So, to take the discussion forward in understanding the correlation between the wave function in position space and momentum space, first I want to spend a little bit of time trying to understand what is a Fourier transform. Now, this is a very complicated, detailed topic. I want to give you a very concise, simple explanation of what's happening here. So, let's keep this to the side. Let's come here to the right side of the board. What is a Fourier transform? A Fourier transform is a mathematical method or a mathematical tool of studying functions or signals with respect to different domains. You see, here we have some kind of a function or a signal in terms of some kind of a variable, like let's suppose time or space or frequency. So, when we try to study the same function in terms of different variables or in terms of different domains, then we enter the subject of Fourier transform. For example, here I have a Fourier transform between, let's suppose, time domain versus frequency, or more specifically angular temporal frequency domain. So, what is time domain? Time is t. Angular temporal frequency is omega. So, what is omega here? Omega is just the angular frequency, or to be a little bit more precise, I am calling it angular temporal frequency, which is 2 pi nu, where nu is the frequency and nu is related to time period of a signal. So, essentially what we are trying to do here is, we are trying to understand the relationship between a function of omega versus a function of time, and that is what we are interested in. All right. So on the left hand side, I have a function with respect to time. So this is the time axis and this is a function, and as you can clearly see, it is a sinusoidal function. So I can say something like sine omega naught t. All right. This is a sinusoidal function having one distinct frequency. So if I want to look at this particular signal in a different or with respect to a different domain, so here I have, let's suppose, capital F omega, and this axis is the angular frequency. Then because the signal contains only one frequency, therefore in this graph I will get just one line. Where? At omega naught. That's it. Make sense? We have a sinusoidal function having one distinct frequency. So this is how it looks like in terms of the time domain. But if I look at the same signal, but in terms of the frequency domain, then I just get a simple distinct line here at this particular omega naught. So this is known as the Fourier transform of this particular function. They look different from each other, but if you understand what's happening, it makes sense that with respect to the frequency, you'll get just one line because there's just one frequency present here. But with respect to time variation, it will look something like a sinusoidal variation. Now, ideally speaking, in ideal cases, we should get a delta function. But in realistic scenarios, we can't really take a signal from minus infinity to plus infinity. We usually take it in a finite sort of a region or finite range. Then we end up getting something of having a line which has a slight width to it. But I don't want to complicate the discussion to avoid complications. This is a simple representation of a signal in terms of time and signal in terms of frequency. Now let's take this a little bit further. What if I have a little bit of a complicated sinusoidal function? So instead of a simple sine function, let's suppose I have the sum of multiple sine functions or multiple frequencies. So let's suppose I have something like sine omega naught t, all right, one frequency, plus twice sine, let's suppose, 2 omega naught t, another frequency, plus let's suppose sine 3 omega naught t, another frequency, and plus let's suppose twice sine 4 omega naught t. So this is some kind of a summation of 4 distinct frequencies. So if I look at the Fourier transform of this particular signal with respect to the frequency domain, then what should I see? I should see 4 distinct lines. So these 4 distinct lines corresponds to omega naught, 2 omega naught, 3 omega naught, and 4 omega naught. So this is the very brief description of how we can look at a function or a signal in terms of time domain versus the same signal in terms of the frequency domain. So this transformation between the time domain to the frequency domain is what is called Fourier transformation. Now we can take this a step further. You see here we have a distribution of a function in terms of the time domain. Here we have the distribution of the same function but in terms of the frequency domain. We can take this a little bit further. What we can do is we can add up large number of sinusoidal waves so that we end up creating some other recognizable function. So for example, here we have a distinct number of sine waves that when taken in appropriate wavelengths and frequencies ends up giving us a square pulse or a pulse wave. So this is something that you probably have studied when you studied Fourier series. So we can use a certain kind of a Fourier series technique to generate square waves, sawtooth waves, and other kinds of periodic functions. So what I'm trying to say is that we can take a large number of sinusoidal waves to generate other known functions, and then that will have a corresponding distribution in the frequency domain. And there are already large number of standard problems where we can look at the Fourier transform between the distribution in time domain versus the distribution in terms of the frequency domain. Many of them are given here in this particular chart. Now, how is all this relevant to our discussion? Well, I'm coming to that. That's why I'm trying to talk about the Fourier transform in the first place. But this general mathematical tool of transforming a function or a signal from one domain to another domain is associated with a particular expression which is relevant for us. So, for example, if I want to write down the function which is basically with respect to the time domain small ft, then I can generate that function mathematically if I know the functions in terms of the frequencies, okay. So, mathematically speaking, this is equal to 1 upon, let's suppose, 2 pi, and if I add up or integrate all the frequencies, which is f omega e to the power minus iota omega t, and then I integrate it with respect to t, then this would give us the left hand side of our figures. Similarly, I can also obtain capital F omega, mathematically speaking, from small ft, which is equal to 1 upon root 2 pi minus infinity to plus infinity ft e to the power iota omega t. Wait, this should have been d omega, sorry. This is an integration with respect to d omega, and this is an integration with respect to dt. So here, what is interesting is that the second function, capital F omega, is a Fourier transform of small ft, and small ft is a inverse Fourier transform of capital F omega. Now, it is not necessary that we always have to do the transformation between time and omega. There are other domains with respect to which we can look at a Fourier transform. So, for example, we can look at, let's suppose I call this point number 2, space versus angular spatial frequency, okay? Angular spatial frequency. So, space means if a particle is in motion with respect to the x-axis, I call it x or position, and angular spatial frequency is k, also called as the wave number. See, whenever we look at these kinds of periodic functions, it may have a certain periodicity with respect to time. So, when we look at the frequency in the time domain, that's called angular temporal frequency. But there can also be a periodicity in the spatial domain, in space. So, then we talk about wavelength or the wave number associated with the wavelength, or more precisely angular spatial frequency, or k. So, we can look at a function in terms of position and wave number, and we will have a Fourier transform having a similar sort of a mathematical expression. So, I can have some kind of a function, let's suppose I say f of x will be equal to 1 upon root 2 pi from minus infinity to plus infinity, and then you have some kind of a function f, let us call this as k, okay, e to the power, you will have minus iota k x, and then you have d k, all right, and its Fourier transform will be f k will be equal to 1 upon root 2 pi from minus infinity to plus infinity. Here we have small fx e to the power iota kx integration with respect to dx. So, here this is the Fourier transform of a function in position domain. We end up getting a function in k space, and then this is the inverse Fourier transform. I want to give you a little bit of a example of this. So, here I have a website which enables us to do a Fourier transform between k space and position space. It's a very interactive website. I'll link its, I will give its link in the description. So if you're interested, you can check the link. So as you can see here, in the first graph, in the topmost graph, we have this distribution of the waves in K space. All right. So essentially a distribution of the wavelengths, you can say. So there are a large number of signals or sinusoidal functions having distinct wavelengths all added together in different proportion. So this basically gives us an idea about the proportion. The second graph is just a superposition of all the waves. And the third graph is the Fourier transform. So therefore, this is a signal in position space. So the first and the third graph, they are Fourier transform of each other. So you can think of the third graph as the graph in position space and the first graph as the graph in K space. Now remember that in quantum mechanics, K is essentially related to momenta, okay, because P is equal to h cut K. And if I make some changes to it, so let's suppose if I change the spacing, I can increase the spacing or decrease the spacing. If I decrease the spacing, then I see that I end up getting a sort of a larger number of waves that superimpose to give me a better sort of a wave packet. So this is, at this particular point, I have kind of zero spacing between, so I have an infinite number of sinusoidal waves having distinct wavelengths or wave numbers. And at the bottom, I have a wave packet. The reason I've chosen this is because this is a perfect example for a Gaussian wave packet. So we have described earlier when we were talking about what is the representation of a particle in quantum mechanics, then we use the concept of the wave packet. So if the particle is going from one point to another, then it has a wave packet associated with the particle's essential solution of the Schrodinger equation. And if the wave packet evolves as it goes from one point to another, we can figure out the other physical properties of the particle. So here is the third graph. There's a wave packet associated with the particle's probability distribution in the position space. But then the first graph is the distribution of the particle's wave packet in momentum space or in K space. And they are both related to one another. They are Fourier transform of one another. All right, how can we know that? We can change the width of the wave packet. So if I decrease the wave packet width in the K space, the wave packet width in the position space increases. If I do the reverse, position space wave packet width decreases, and like this. Does this remind you of something? What does this remind you of? This should remind you of the uncertainty principle. You know, the uncertainty principle says that the uncertainty in the position of the particle in quantum mechanics is inversely correlated to the uncertainty in the momentum of the particle. So the width of these wave packets are associated with the accuracy with which we can figure out the momenta or the position of the particle. And because quantum mechanical formulation is fundamentally distinct from classical mechanics, in classical mechanics, particles have a definite position and a definite momenta which are related by a very simple mathematical expression. In quantum mechanics, we don't have that. We have wave functions in position space and wave functions in momentum space. And because of Fourier transform, both these wave functions are inversely correlated in terms of its width. So when I try to find the position of a particle more accurately, there is greater amount of uncertainty in its momentum. When I try to find out the momentum of a particle more accurately, there is a greater amount of uncertainty in terms of its position. So I just wanted to show you this because it's a little bit of an interesting interactive simulation. Coming back to our discussion, we have a similar sort of a scenario in the context of quantum mechanics. Now, this is the Fourier transform between time and angular temporal frequency. This is the Fourier transform between space and angular spatial frequency. Now let's come to our wave function. You see, when we talk about a wave function, the wave function is essentially a solution of the Schrodinger equation, which is a function of position and time. What I'm saying is that this function of position and time has a Fourier transform in K space or momentum space. Because what is momentum? We know that in quantum mechanics, P equals h cut K comes from the de Broglie hypothesis. So when we talk about K space, we are essentially talking about momentum space. So let's look at the wave packet of a particle in quantum mechanics. So here I can simply say that what is psi xt, okay. Now usually wave packet is the most simplest sort of a description of the particle in terms of a Gaussian wave packet. Of course, depending upon different scenarios, it could be very different, but I'm trying to give you a sort of a general sort of a correlation. So for that, I'm just going to take the wave packet as we have described earlier in the earlier lectures, is essentially equal to 1 upon root over 2 pi h cross from minus infinity to plus infinity phi k e to the power iota kx minus omega t dk. Now, I have discussed this in detail previously when I was talking about wave packets and we were discussing those concepts. But let me just explain what is this e to the power iota kx minus omega t. It is just a plane wave. All right. What is phi k? Phi k is some kind of a modulating function that modulates the essentially wave numbers and the wavelength. So essentially we end up getting a scenario in which we are adding up a large number of plane waves having different wave numbers, and then we are integrating this with dk. That's what it is. This expression 1 upon root over 2 pi h cross is, I have put it essentially for purposes of normalization. We know that wave functions have to represent physical particles, and therefore they are directly correlated with the probability of the particle being found in some region, which accordingly is governed by the Bond's statistical interpretation. So there is a concept of normalization which we have discussed earlier. For those purposes, we have to keep a constant here. But essentially, this is what the wave function solution of a Schrodinger equation is in terms of the plane wave solution sums. But let's suppose I want to consider this at time t is equal to 0. So at time t is equal to 0, what do I have? I have x, phi x at time t is equal to 0 comes out to be 1 upon root over 2 pi h cross, goes from minus infinity to plus infinity, phi k e to the power iota kx dk. Now, I can do a Fourier transform to obtain phi k here. Should I do that? If I do that, phi k comes out to be 1 upon 2 pi h cross integration from minus infinity to plus infinity phi x or psi x e to the power minus iota kx dx. This is the wave function which is a solution of the Schrodinger equation in position space. This is the wave function of the same particle in momentum space. But because k is equal to p upon h cut, right? K is equal to p upon h cut, I can make those necessary substitutions here, and I can say that this is essentially equal to iota, right? I can say that this is iota px upon h cut, and I can say this is equal to minus iota, okay? I can say that this is minus iota px upon h cut. And essentially the h cut here comes because we are integrating not in terms of k but in terms of p. I should have mentioned this before, okay? So this is basically a function of p here. And the moment I go from k to p, that is how this h cut comes here in the normalization constant. Okay, so this is supposed to be p and p. Okay, the moment I substitute k with p, there is a 1 upon root over h cut that comes here. So if by making the necessary changes, the resultant expression comes out to be this. So this is the wave function in momentum space. So as the particle evolves in the quantum mechanical world, we don't really know its exact position. We do not know exact momentum, but we have a function that contains all that information. So we can analyze the system either by looking at the function in terms of the position space, or we can also analyze the system by looking at the function in terms of momentum space, because even this function has the capacity to provide us information about the probability distribution and other quantities like expectation values of position, momenta, etc. So let me explain that by rubbing this portion of the board. Okay. So once you have this function, we can use it to find, for example, the probability density of the particle in momentum space. All right. So how do we do that? The usual. You take phi, which is a function of p, and you do mod square. You take its complex conjugate, multiply it with the function, you end up getting the mod square. This gives us the probability density of the particle in terms of the momenta. So for example, if I want to find out what is the probability that the particle having momenta or momentum between, let's suppose, two values p1 and p2, right? With respect to the wave function in position space, what questions we used to ask? We used to ask what is the probability that the particle will be found between one x and other x value. Okay, what is the probability the particle will be found in this region? But in the context of the wave function in momentum space, we ask what is the probability that the particle will have a momenta between one value and another value. So essentially, what is the probability the particle will be going with a velocity in a given range? So that comes out to be integration between p1 and p2 of the mod square of this dp, the usual. All right. Similarly, we can also talk about expectation values. All right. Now, what are expectation values? Expectation values are essentially average values of position, momenta, energy of a particle, because we can never really know what is a definite value of these quantities for a system unless we actually make a measurement. And making a measurement in quantum mechanics is like gambling. You never really know what you're going to get before you actually make the measurement. So after you make the measurement, you get some value. But if you repeat this process in different similar systems over and over again, you get large number of quantities. You get different numbers. You can take the average, and that is the average which can be predicted theoretically speaking. So in position space, so let's suppose first I want to make a comparison with in position space, what are the expectation values, and then I want to look at in momentum space. Okay. So in position space, if I wanted to find out the expectation value of, let's suppose, position itself, do you remember what is its expression? Its expression is usually integrate. You have the wave function in position space, x, complex conjugate here, x SI dx. That was the expectation value of position in position space. But in momentum space, the expectation value of momentum is equal to integration between minus infinity plus infinity of this wave function, which is phi complex conjugate p phi dp. This will give us the average of the momenta of the particle. Similarly, if I want to find out the average value of the momenta but using the psi, then what we do is we insert the operator of momenta here, sandwich it between the wave functions, minus iota h cut del upon del x psi dx, right? But in the momentum space, if I want to find out the expectation value of position, then we do the reverse. So essentially, you have phi star and you sandwich iota h cross del upon del p, and here you have again phi and dp. So this will give you the expectation value of the position, but with respect to the wave function in momentum space. So you can see that these are kind of, it looks like the mirror image of the expressions of one another. Here you have a minus iota, here you have a plus iota. So essentially this formulation gives us all these possible expressions that if you, instead of dealing with the wave function in position space, if you have calculated the wave function in momentum space, then also you can figure out so many different things about this particular system, because at the end of the day, both the wave function in position space and the wave function in momentum space are Fourier transform of one another. So if you understand one, you understand the other. So this kind of a scheme is known as momentum representation in quantum mechanics. Now to extend the discussion a little bit further, I want to actually solve a problem. If you are interested, you can continue. I will give you a numerical problem which is somewhere here, and I want to actually solve it and obtain the answer for this particular problem based on the expressions that I have just now obtained. So in this question, we have a particle of mass m which is represented by this wave function. Psi is equal to a e to the power iota k naught x in the range of minus a to a, but 0 otherwise. Find the corresponding normalized wave function in momentum space. Very simple, very standard question where you are given a wave function in position space and the question is simply asking you to find out the wave function in momentum space. I'll just show you how to do it so that you can do similar questions if you face them in any examination. Now the thing is, first we need to normalize it. Okay, we have this normalization constant a, and first we need to normalize it. You see, whenever you normalize a wave function, let's suppose in the position space, the normalization remains intact as you go into the momentum space. So if I normalize it once, I'm fine. I'll get the answer as normalize itself. So how do you normalize it? You take psi star, psi dx, go from minus infinity to plus infinity is equal to 1. That means the probability of the particle being found in the entire universe along the 1D is exactly equal to 1. But because the particle doesn't really exist beyond minus a and plus a, the wave function is anyway 0. So therefore this integration can be written between minus a to plus a, and then you have a star e to the power minus iota k naught x complex conjugate a e to the power iota k naught x dx is equal to 1. Of course, these two terms gets cancelled and all you are left with is a star times a is a mod square from minus a to plus a dx is equal to 1. This becomes what? A mod star a mod square is equal to, you end up getting x from minus a to plus a equals 1. This becomes a mod square, you have a minus minus plus a equals 1. So finally we end up getting a mod square is equal to 1 upon 2a, but because it's a real number, I think I should better say capital A is equal to 1 upon root over 2a. This is the normalization constant. Now if I want to find out the wave function in momentum space, okay, then I'm going to simply use the expression that I just mentioned a few moments back, which is phi p is equal to 1 upon root over 2 pi h cross, all right. And then we have psi x e to the power minus iota px upon h cross dx between minus infinity to plus infinity. Again, I can write the limits as minus a to plus a here. So if I just substitute everything, what should I get? 1 upon 2 pi h cross between minus a to plus a. We have psi x. Psi x is, again, the a expression is 1 upon, so here I have 1 upon root 2a and e to the power iota k naught x, and the remaining terms are e to the power minus iota px upon h cross dx, all right. So everything else that follows is simply a mathematical calculation. 1 upon root over 2 pi h cross times 1 upon root over 2a minus integration from minus a to plus a, you have e to the power. If I take let's suppose iota as common, you have k0 minus p upon h cross x dx. So this is just integration with respect to x, where k0 is probably a constant and p is related to k0. So I can simply do a standard sort of a result. I can show that this is equal to 1 upon 2 root over pi h cross a. This is going to be equal to, if I do an integration of an exponential function, I should get here iota k0 minus p upon h cross 1 and e to the power iota k0 minus p upon h cross x between the limits of minus a to plus a, which becomes, again I have to simplify this whole expression, this becomes 1 upon 2 iota, you have pi h cross a k0 minus p upon h cross, and here I have e to the power iota k0 minus p upon h cross a minus e to the power minus iota k0 minus p upon h cross a. All right. So here I can simplify this entire expression by using a identity. What is that identity here that we can use? The identity that we can use is e to the power, you have iota theta minus e to the power minus iota theta upon 2 iota is essentially equal to sine theta. So if I use this here, then what I can do, so 2 iota will get absorbed here, and then this is essentially going to become, if I write h cross k0 minus p, then h cross and so root over h cross will get cancelled, and I'll get here the final expression will come out to be root over h cross, and then you have root over pi a, and then you have h cross k0 minus p, and here you have sine k0 minus p upon h cross a. That's it. This is the wave function in momentum space corresponding to the one that has been given to us in the question. So we have found out the wave function in momentum space corresponding to the wave function in position space that was given to us. And if the question asks us any further inquiries in terms of probability, in terms of expectation values, we can proceed from here in terms of the expressions that I have given. All right. So this is just a very simple standard question. I thought I will solve it so that you get familiar with the topic. Many people, many students are not really familiar with this particular simple topic, but it's actually not that difficult. All right. That is all for today. I will see you next time. Thank you. Take care. Bye-bye.